Hey everybody, it's Taylor. Today we're going to talk about using units in Python. In scientific computing, it is really important in many instances to keep track of units. In fact, some of the great engineering disasters out there have been related to units, believe it or not. Take the Mars Climate Orbiter, right? This was back in 1999. It was a spacecraft, right, that was around Mars. But when the people back at Mission Control sent it a command, they sent it with the non-SI units of pound force seconds, barbarians, when it was expecting the units in SI units of Newton seconds. And so it got the wrong amount of force, and so it actually went too close to the planet, and they think that it was either destroyed upon in the atmosphere of Mars, or it got sent into heliocentric space, leaving Mars' atmosphere. So in either scenario, it was a disaster, and it was because of units. So we've got to keep track of units. And if you've used something like Wolfram Alpha, you know it can do really cool stuff. Like you can tell it to, hey, go from 5 centigrade to 5F. No problem, right? And it can do that. But it can do more complicated things, right? If you use Wolfram Alpha, you can tell it like 60 miles per hour per joule, right, if you want, to kilometers per second per electron volt. Technically, those are like nonsense units, right, for some funky situation, but it can still give them to you. It can still do these conversions, right? So, yeah, kilometers per second per electron volt joule, right? So if you want to, there are software programs out there that can do these conversions, but when we are writing our software, our little code snippets, we want to be able to do them too, right? So how do you do them in Python? There's several different ways. One way to do it, I found a library called unit conversion. So from the library unit converter, from unit_converter, that module, we're going to import dot conversion converter. We're going to import convert. Okay. So this is one way to convert things. We'll call it just a simple conversion tool for one-time conversion. This might be what you're looking for. Okay. How it works is we're going to give it the command convert, which we've just brought in, and then it says quantity in a string format to the desired unit in a string format. So it just wants two strings, right? And here they give an example, right? 2.78 DAN times millimeter squared to MN, millinewtons, towards micrometer squared, right? It would convert that out. Let's do a different one. Let's do, we'll do 60 meters per second, right? We want to convert that to, let's do kilometers per hour, right? If we want to make that conversion. So let's go ahead and run that. If we run this whole thing, we get an error. It doesn't know it. It doesn't like the. It doesn't like that we called it HR. Let's just try H. Okay, so it looks like it ran that. Let's see what it does by just highlighting that and hitting F9. And sure enough, it spits out the conversion right there. 60 meters per second is equal to that number in kilometers per hour, right? So this is a pretty simple tool that works for a lot of things, but it's not the most powerful. What we would really like is when you're writing programs, you've got x equals, it's some variable that equals 5, maybe gallons. So what we'd really like to do is store this as 5 gallons, right? So that we can use it in our code and come back to it and pull out the 5 or change the gallons to something else. How do we do that, right? To do that, we need to bring in a different library. This one's called pint. We're going to import pint. By the way, these are custom libraries that did not come standard with this installation of Anaconda, but it's really easy to install them. You're just going to go to your start and you're going to type Anaconda, and when you get to this Anaconda prompt, right, this allows you to do pip installation. So you could just do pip install pint. That's it. That will install it. When I hit run, first off, it's going to tell me, hey, you've already got it. So it's going to say requirement already satisfied, like you've already got pip, or pint, I mean. So I don't need to do anything. And if you don't like it, if you install a library that you don't like, you can just do pip uninstall pint. And this will give me the option for uninstalling it. Now, since I want to use it today, I'm not going to uninstall it. So when it says, do you want to proceed, yes or no, I'm going to say, no, I don't want to get rid of it. So I'm going to keep it. All right, so that lets me to have pint. Now, pint lets you do some really cool things. Pint has what's called a unit registry. So I'm going to make a new variable called u, so I don't have to type out this unit registry every time. So u is equal to pint.unit registry. Okay. So this method allows me to do some really cool things. It allows me to keep track of the quantity and the unit, right? The magnitude of something and the units associated with it, right? We're going to bring in one other thing. We're going to do q equals u dot, where u is now this pint.unit registry. we're going to bring in quantity function, okay, or the quantity method. Okay, we're going to use both of those. Now here's how you use them. Let's say that we want to store a value. Oh, it's giving me an error. That's because this needs parentheses right there. Okay, let's try that again. Great, now it's working. So let's try and do the same conversion that we did up here, but we're going to do it using pint, okay? So let's go ahead and just make a variable called speed, right? So our speed is equal to, we're going to use this q command, right? Which is really doing pint.unitRegistry.quantity, right? It's making it very simple. With the simple value of q, we now can type in two things. We're going to type in the value, so we're going to do 60, and then the second thing that it's going to expect is the units, so meters per second. So as a string, we're just going to do meters divided by seconds. Okay? I don't think you have to type out meters. Let's try that and see if it works for us. Okay? So let's test it now. Let's come down here in our console and type in speed.units. Right, and this is going to return the units of that. Now, unfortunately, I've got this dark background in Spider, and when this library by default writes the units in black text, so it's hard to see, but hope you can see that it says meter per second there. So great, it knew that m is meter, right? That it knew that notation. Great. Now, it's really simple to do a conversion. We can just write print. Okay, we're going to do speed and then .2, right? So this method 2 allows us to make the conversion where we just type in the units that we want. So it could be inches per hour, right? If we want. Let's run it. So it takes it in 60 meters per second and it's going to print it into inches per hour, and it's this number down there. So how slick is that? Really, really powerful tool. Now what if you don't want this whole string to get outputted, but you just want the number part of it? Easy peasy. We can do that too. We could come and we could just type speed dot magnitude, and it just returns the number part, not the units part, right? The magnitude. And again, it kept it in the original form. So we did this speed 2 and we converted it to a different form. That did not resave it over the initial speed variable. It just did a inline conversion of it from one unit to another. Okay, so that's the basics of using pint. Let's do some examples. Okay, let's take two units, right, two variables that each have units, and try combining them either by multiplying or dividing. Let's take this. Let's take distance equals, I don't know, we're going to use our q command, right? That means that we're declaring a variable that has a quantity and a unit associated with it. So let's say that it's 8, we'll say meters. Okay, so we now have a distance. Now let's take time, where time is equal to, again, we're going to use q because it's going to be a quantity, let's say 15 and then seconds. Okay. Now let's take speed is equal to distance divided by time and run it and see what happens, right? So we run it, we've now overwritten speed. Okay, so let's go ahead and grab this print column and bring it down here and see what it does now. So let's do it in meters per second. Meter per seconds. Run that, and it should be 8 divided by 15, or roughly half, 0.533 meters per second. Great. So how cool is that? It's able, you can store these things, multiply them, divide them, and it knows what to do with the units as well. So that's something really great that Pint can do. If we wanted to, we could resave this in our speed variable. We can say speed equals speed.2, and then we could do unit dot, let's say, kilometers divided by unit dot hour, right? If we want to do that, we could. When we come down here now, let's go ahead and reprint it again after doing that. So let's test it down here. Now when we go to it, we go to speed.magnitude, and sure enough, that is the value in kilometers per hour. Let's make sure that that's the right unit. We're going to go to speed.units, and again, sorry for the black text, but it's in kilometers per hour. So pretty slick. Pints is really pretty powerful. Let's do another example. Okay, for this one, we're going to bring in some other constants. For that, we're going to bring in another library. We're going to bring in scipy. So we're going to import scipy. That's for scientific Python. We will do lots more of that soon when we get to solving equations. But from scipy.constants, we're going to import the scipy.constants as CNST. We'll just call it CNST. Okay, so this allows us to bring in constants. Well, what kind of constants? Well, we could say that c, the speed of light, is equal to CNST. That's scipy.constants .c. That is the default value for the speed of light. So let's go ahead and run that. If we come to our variable explorer, Okay, let's check it. Over here in our value for C, it's a float, and it is just this value. So interestingly, with scipy, when you bring in this constant, it doesn't have units. It just gives us the value of that constant, right? The value of the speed of light is 2.9979 e to the 8th. All they have is the float and not the units. So let's go ahead and take this constant and let's give it units using pint. So we're going to combine these two. We're going to say that C, our speed of light, is not just equal to the constant value. That's just the quantity. We're going to use this quantity method from pint, where the value needs to be the value from the scipy constant, but the units need to be, we know that's in meters per second, right? So let's go ahead and do that. Run it. Now, if you look at this, our C is no longer just a float. It is now this quantity, which is a pint class, right? It's the build quantity class, okay? And if you look at it, we would find under magnitude, gotta scroll all the way down inside these fields of the class. Inside here in our magnitude, you'd see there's the value, right, the magnitude. And then if we looked under units, we would be able to see the units. So under units, we would be able to see what type of units it has. I think you have to click that open, okay? All right, so let's go ahead and figure out how far you could go in a light year. What's the distance of a light year? Well, it's the speed of light times 1 year. All right, so we've already defined our constant for the speed of light, and we've given it units. Let's define a light year. So a light year is equal to, it's going to be C multiplied by, now we need to define 1 year. We haven't made a variable for 1 year, but we can do it right here in line. We're going to do the Q command, right? Our function from pint that creates a registry, right? A quantity. So that's going to be 1, and then the comma for the units will be year. So now we've defined our light years, so these are multiplied together. Now we can go ahead and convert it. We can go ahead and print. We're going to print the value of a light year, and we're going to do the to command. We're going to convert it to just, this should just have the units of meters, right? Because the seconds and the years can cancel out with the correct conversion factor, and the to function knows how to do that. So let's go ahead and print it, and sure enough, we find that, yeah, a light year is that far. It's a very large number of meters, okay? So that's pretty great command that we can do. Let's do another example. For this one, we're going to bring in chemical information. So we need a new library that stores things like elemental masses, right? The molar mass of the different elements. Because a lot of the conversions that we do in material science have to do with chemistry. So from that, we need a new library, and that library is called molmass. So we're going to import molmass, and from molmass, actually, we're going to import, it's called formula, capital K, formula. So this allows us to do some really cool things. So let's come down here for this example. Let's say that we want to ask the question, what is the density of sodium chloride if the lattice parameter 563 nanometers, okay? Well, we can go ahead and do this. First off, we need to say, let's see, formulas per cell. We're going to make a variable because this is the rock salt structure. We know that there are 4 unit cells, or 4 formulas per unit cell, so that's going to be 4. So now we need to know, if we're going to figure out the density, right, density is equal to mass divided by volume, okay? So we haven't defined mass or volume yet, but we can. What's the mass going to be? Well, the mass is going to be the weight of each formula, and there's going to be 4 of those, right, divided by Avogadro's number in order to get that in the right units. So mass is going to be, what is the mass of NaCl? Well, you could look it up, or we can use this really great library, molmass. And this formula command, let's go ahead and do it. Let's say that NaCl, we're going to have that equal to formula.NaCl, and you can see in the help, they tell us what they're looking for. It's looking for a string that represents chemical elements, isotopes, parentheses, numbers. It's asking for us to put in the formula. So for this one, we can just put in NaCl. So we've stored that. Now, once we do that, the mass is equal to NaCl.mass, okay? So let's comment this line out for just a moment. Okay, so let's check it so far. What do we have? When we run this, let's come up here to our mass is equal to a float, and that will be the value in grams per mole. Now we probably want to divide that by Avogadro's number to get the number of grams, okay? So we can do that. So this is going to be divided by Avogadro's number. Well, fortunately that comes from scipy. So if we have our constant, right, that we brought in from the scipy library, constants, then we're going to type in Avogadro's, Great, it knows what we're looking for, so it helps us finish it. Now we need to have the units here, so let's go ahead and give this units as well. So this first one, the mass is going to be in what? That's going to be in grams per mole. So let's use the quantity method, right? The value is that. The units are going to be grams per mole. So that's our first quantity. Now the quantity for Avogadro's number is going to be Q, again where it's the value of Avogadro's number we get from the constant. Now we need to give the units, which is 1 divided by mole. Okay. Alright, so now we have stored this mass, right? So now let's go to do our volume. How do we know what the volume is? Well, it's rock salt, so it's a cubic crystal structure. That makes the volume really easy. The volume is just going to be equal to, again, we're going to do the Q command for quantity. That allows us to work a number with units. So this is equal to the lattice parameter, 0.563, and the units for that are nanometers, okay? This needs to be cubed, so we do that, multiply, that means take the exponent. We're going to cube that. That gives us volume. And now we are ready to define our density term, which is mass divided by volume. Finally, let's go ahead and print our density dot 2. Okay, we're going to convert this to, let's say, grams per centimeter cubed. Okay. Oh, this is capital volume, and this was lowercase over here, so it wasn't liking that. Let's try that again. This time it's going to print it out, and if we did this correctly, something's not quite right. What do we miss? So this is not the right number. Salt is heavier than that. This would be salt that floats, and it doesn't. What are we missing? Well, under mass, so we have here we have the mass of salt divided by Avogadro's number, but we forgot to multiply it by the formulas per unit cell. So we need to include that. So let's grab this, and this needs to be multiplied by that. Okay, let's try that one more time, and it should print out the density of salt now. Yeah, there we go. 2.17 grams per cc. Let's check to see if that's right. Density of NaCl, yeah, 2.16 grams per centimeter cubed. So here you can see a really powerful tool to bring in this chemical information for units, bring in constants from scipy, bring in unit conversions from pint, and working together you can get it to do some pretty slick stuff for you. Alright, let's do two last examples. One is we can define our own units. If while you're working you come up with, you want to be able to work with your own custom units, great. There's this story of this guy at MIT, right? Smoot. If you haven't looked this up, it's kind of interesting. An MIT Smoot unit. He was a kid, I think in like a fraternity, and as a prank, they used him as a measurement of length, like however long that person was, and so they did this measurement out to the bridge. In any case, he is now an official unit. It's equal to 1.702 meters. So we can define that as a custom unit in Python if we want using pint. So we're going to do custom units, right? So we're going to do u.define is the function now, and we're going to call it a smoot. So 1 smoot is equal to 1.702 meters, and then you can even give it like a shorthand, right? We can call it SM for smoot, okay? So now we've defined a unit in smoot, so we could take a quantity, right? We could print the quantity, well, let's make a variable. Our distance from before, right? 8 meters. Let's go ahead and convert that to smoots, right? Great, so we can print, we're going to print distance.to, and it's going to be in the units of smoots, right? So let's do that, and when we print it out, it tells us that 8 meters is equal to 4.7 smoots, right? So you can define your custom units. Okay, last thing we want to cover is an example of just another calculation. Let's do one for electrical conductivity. Oops, let's get that out of the way. Electrical conductivity. Now there's a formula where we know that sigma, the electrical conductivity, is equal to N, the carrier concentration, multiplied by the mobility, multiplied by the charge, right? So let's go ahead and do that. Let's define these things. We'll say that N is equal to, we're going to use Q because it's a quantity. It's going to be, let's say it's like 1 e to the 17th. So you can use scientific notation here, that's no problem. And then we have to give that its units. That has the units of centimeters to the -3. So that allows us to define our concentration. Now let's define our mobility. Now I looked this up ahead of time, and the mobility, we'll call this mu is equal to Q. It's 1.5 e to the 4th, and that has units of centimeters squared per volt per second, right? So I looked that up for silicon. That's the mobility of an electron. in silicon at this concentration of our carriers, right? Now the last thing we need is our charge of an electron. So we're going to say E is our charge of an electron. We're going to do CNST constants dot E. That is in the scipy library. That's one of the constants. That's the charge of an electron. Okay, but we need to give that units. So we're going to do Q. Okay, and then tell it the units, right? And that is coulombs. Okay, great. So now to go ahead and define our new value, it's going to be sigma is equal to N times mu times E. And now we can print our sigma and we can convert it to whatever we want. So we're going to do sigma dot 2. Let's convert it to Siemens per meter, right? So this is Siemens per meter. We run that out and we see that it's able to convert. Oh, got an error. Oh, it says Siemens is not in the unit register. Let's try Siemens for real quick. Okay, interestingly, it doesn't have the unit for Siemens built in, surprisingly. But that's okay. We know that Siemens is equal to 1 over an ohm, right? So we can say ohms to the -1 divided by meter. Or we could say times meters to the -1, right? It should be able to do that. Great. So yeah, and that's the right number. 24,000 is the one that I calculated ahead of time. So this is just a quick primer on how you can use some really cool tools for handling units, for dealing with them in your scientific computing, which is honestly you're probably going to run into as a material scientist, is wanting to keep track of units. And these are a couple really simple ways to do it. I suggest learning how to use pint. I think it's the best. And we will get into a lot more detail of scipy coming up soon. Okay, stay tuned. On to the next video.